everyone. This is Indradeep Kumar, Assistant Professor, Institute of Aeronautical Engineering in Aeronautical Department. So today we will see the fatigue strength and ascent diagram. In this video we will see fatigue strength and ascent diagram. So the topic will be, first we will see the fatigue strength, then type of fatigue, and then we will see about the ascent diagram. So first, fatigue strength. So what is fatigue? And after that only we can define the fatigue strength. So the stress that can be withstood for a specified number of cycle is called the fatigue. Means up to like we are repeating. So suppose this one is there, we start repeating like this continuously, or by the time when force is acting continuously on any body, that type of load is called the fatigue load. And because of that, how much they can withstand, that is the fatigue strength of that material. Means how many times they can sustain that stress applied over the surface. That is the strength of that material. So we can define like that, what? Progressive deterioration of the strength. So when we will start bending or force is applied, so what happens by the time their deterioration starts? So the progressive deterioration of the strength of material or structural components, whatever we are seeing, in that when progressive deterioration is there, then we can say that is the fatigue. Failure can occur at much lower stress level also, or at higher level stress also, depending upon the fatigue strength of the material. So that's why failure can occur at much lower stress levels than the ultimate stress level. It's not necessary that once any material ultimate stress level will reach, then only it can deteriorate or break. That is for one time. If suppose one time we are hammering, once it will reach to that maximum ultimate stress, then only it will break. But because of the fatigue, that is the number of repeating or repetition of the load, it can crack or get damaged much earlier than the fatigue load. So depending upon how many times stress is acting on that material. So what happens if it's in the direction, or we can say it's a dynamic phenomenon, means it can progress in any direction. It's not necessary that it can be in that particular direction only. So it can be of a small, which is in terms of that micro crack, or that macro crack also. So that means these can be of micro as well as macro cracks. Now if it's not detected, then what happens? Then catastrophic failure will be there. Means from that point the material will start, that crack will start propagating, and finally that material got broken into pieces depending upon how the stresses is there. So now fatigue damage can be produced in a variety of ways. Why? Because just I told you that it's not necessary that in the same manner it will be there. Once crack will start, either it's a micro or macro, after that it starts progressing and finally it will break. So it can start in various way, either micro, macro, in outer surface, inner surface, any type of there, right? Some materials such as mild steel possesses stress level that can withstood for an infinite number of cycles. Means some materials are there like mild steel for that having infinite number of cycle, but some material having one or two. So like aluminum, if soft aluminum wire you will take, you can bend 4 or 5 times and you can see that will break. So that depends on the nature of the material, how many times it can sustain, and that is known as the endurance limit of the material. Means up to what limit or how many number of cycles it can withstand, that is called as the endurance limit of that particular material. So this endurance limit will be different for different material. Now type of fatigue. So first type is cyclic fatigue. That type is low cycle and high cycle. So means the material which breaks or which got broken down into pieces with lower cycle, means like just I told you 4 or 5 times if aluminum soft wire is there, after that it will break. So that comes under the low cycle. And previous slide example was there, the high cycle, that is mild steel, even in finite number then also it can sustain. So that is the high cycle fatigue. Next is corrosion fatigue. So means by the time, just example, iron is there, once you will leave it for a long time, what happen? It start corroding. So once you will remove those corrosion part, what happen? Now whatever the size of the or shape of the iron pieces is there, that will get deteriorated. Means we will not get the actual original one. So that also happens. It's not like that one day it's get corrode. So for corrosion also it requires time. So that is also a type of fatigue. Now, a small scale movement. So when we are just scratching or something, just a small rubbing, like we are erasing something by a rubber, that what happened? That rubber got deteriorated after some time. Once we will use that one, we have to remove that one because now that rubber becomes very small. So that type is called the fritting fatigue. So that is the example of that eraser is the example of fritting fatigue. So means by the time even for a small erasing or a small rubbing, that starts deteriorating. Next is thermal fatigue, means with the application of temperature or thermal energy, whatever these things are there, that deterioration is there or fluctuation in the stress is there, either it can contract or expand. Okay, that is called the thermal fatigue. And for the best example of this is when we can see the railway track, in that when they are joining two tracks, they are keeping some small gap. Why? When during the summer season, because of the temperature, it's got enlarged. So otherwise, if not, then what happens if suppose this gap is not there, this is like this, then that track becomes like this. But if gap is there, then even after expanding, this will be like this. So that is the best example of thermal fatigue. So, okay. Next is sonic or acoustic fatigue, means by applying the sonic sound or acoustic, that means wave, sonic wave or acoustic wave, whatever the deterioration is there, that we can say that is the sonic or acoustic wave. So these things generally we are using in the propulsion system of aircraft. Now here one most important thing is safe life and fail safe structure. Based on that only we are categorizing the structure. That means it will withstand up to that cycle or it will fail before that one. So the first one is the danger of a catastrophic fatigue failure in the structure of an aircraft may be eliminated completely. So means the danger of catastrophic fatigue failure means whatever before it will get failure of that structure, just replace that one. Means now just you are thinking, okay, like we are using for once or twice we use, now remove it before it's a failure. So there is no danger in that one. Or next option is use till you can see now it's start getting cracked or it's start getting failure. So up to that level, right? So from there only the two things came, that safe life and fail safe approach. So now what is safe life? Safe life is the structure is designed to have a minimum life. Remember here the minimum life during which it is known that no catastrophic damage will occur. Please suppose if anything like just you purchase this pen before filling or you have exam, then what you will do? And only half filled pen you have. So that time what you will do? You will change the pen. Why? Just for safety, so that in exam it won't get over and you can use the new pen. So that comes under what? Safe life. It's not like that some small amount of refill inside is there and you will go by that refill to write the exam. So you will change the pen, that is new pen. That is the safe life, right? So before reaching its end, that means before getting refill over, you are changing the pen itself. Means now no tension will be there for getting refill over. So similarly here what happened? Damage will occur, that means before that we have to change. So at the end of this life what happens? The structure must be replaced even though there may be no detectable sign of fatigue. Similarly, if though there is that you can see the half of the refill is filled, but still you are replacing that refill so that during the exam no problem will be there. Means brain that won't get over. So that comes under the fail, that is safe life. Now next example, fail safe approach means the same thing, take pen, same half filled and take another pen also, right? For emergency, if suppose that pen will get over, then you can use the new pen. So here failure also will be there and for safety also you have another pen. Means up to the maximum limit you will use that refill, that which one is you have earlier one, and once that will get over or it's near to over, then what you will do? You will change the refill. So that is the fail safe approach. So in that fail safe approach, what is that? Fail safe approach relies on the fact that the failure of a member in a redundant structure does not necessarily lead to the collapse of the complete structure. Means it's not necessary that you have to completely change the structure. Just you can change the refill also similarly. So here also one or two member of that structure, just replace it. because all the members does not have the same life. Okay, so which some are there which you have to replace earlier, some having a longer lifespan. So by individual member also you can change, right? Complete restructure provided the remaining member are able to carry the load set by the failure member and can withstand further repeated load until the presence of failed member is discovered. Meaning what? So it's no, you can change that one, right? Like just you can see the some car got punctured. Then what happened? They are just with the jack, they are uplifting the car. They are removing that particular wheel only. It's not like that all the four. So all the three wheel is still sustained there. So to stable the car the structure. So similarly here means what? Now whatever the load is distributed by the that particular wheel is distributed among the other three. So that should be withstand, then only you can change the tire. Similarly here, if that members load whatever they were experiencing earlier, if it's getting distributed by the other, then only we can change that load. Similarly, like punctured tire. So if those three wheels are getting experience that force and balancing the car structure, and hence we are just uplifting the car and changing the tire. So now what happened? New tire got changed. So similarly here the last line is presence of the failed member is discovered. So this failed that puncture tire is changed. So that is the fail-safe approach. In that what happened? Such a structure is called a fail-safe structure or a damage-tolerant structure. It's not like that because of one tire got punctured and you will change the whole car. No, that is damage tolerance. You have the puncture, just repair it and you can use again. But if instead of the other some other part will be there, that time might be you have to change that particular part. But in case of punctured, you have to just repair it and you can use it. So same way that comes under the fail safe structure. Okay. So now generally it is more economical to design some part of the structure to be fail safe rather than to have a long safe life. Just like example of the tire, right? There is no, if puncture is there, then no need to change the tire. You can just repair it. So it's not necessary the all the part will be of the same having the long safe life. Some are there, it's got punctured, repair it, you can use it, right? So those lighter parts can be of directly the fail safe approach that we can apply there. Now come to ascent diagram. This diagram is very important when we are investigating about the structure, right? Because earlier we discussed it's because of the fatigue what happened, load is there up to what limit it can sustain. That means up to number of how many number of cycle it can sustain, right? So ascent diagram, that's why ascent stands for stress here, and N is for number of repetition, how many times that load applied on that material. So once we will see this curve, like so this curve is for failure stress and along the x-axis is number of repetitions. So after drawing, so just see in the starting when there is no repetition, that is, or you can say at zero load or zero number of repetition, this is there. Once the number of repetition starts, so just see once repetition starts, this is starting what? Decreasing, decreasing. So just see at this at 100 cycle, this is 100 cycle. So now what is the failure stress? This only, right? So up to this. So now just see after 100 cycle by this amount, it got decreased. Earlier without using, if this is this much stress if you will apply, then only that structure got damaged. But after 100 cycle, only at this stress, that number will get fail or that structure will fail. So now come to 1000 cycle, right? So at 1000 cycle, now just see here. At this stress only, once you will use the 1000 times of that one, at this stress, only once the stress level will reach to this level, that material or that body will get cracked. Come further for 10,000 cycle. Now just see here. This one. So after using 10,000 times, okay, at this only it will get failed. And so on like this, it's continuously going on. Means as the number of repetition increased, yes, the failure stress, that is the amount of stress required to fail, starts decreasing. So this is very important in terms of finding the how many times we can use that structure or material. So by this only we can identify. So this is SN curve for some material, right? So in this curve, just see here, this is for mild steel and this is for aluminum alloy. So already we discussed that mild steel having almost infinite. So just see, after this, once you reach around 10 to the power 5, that is almost 1 lakh, then what happened? It star is remaining constant. So as number of cycle increases, 10 to the power 7, 10 to the power 8, and it goes like this. Means even after applying the 10 to the power 8 times load or 10 to the power 8 times stress, still it's not getting failed. But aluminum alloy, so just see here, once you will increase, then it's coming towards the failure of this one. So that is the difference between mild steel and aluminum alloy. It's not necessary that mild steel and aluminum alloy, depending upon the nature of material. So mild steel having infinite, so it will goes like to infinity. Like rubber is there or any plastic material is there, that time the same will be lesser also. Okay. Next, stress and minimum. So just see stress versus time graph. So this is our reference, or you can say the sigma mean, that is mean stress is this one, right? So this is the amplitude of the mean, that is this is amplitude, or similarly this is in positive direction sigma amplitude, and from here to here this is the maximum, that up to this top is the sigma maximum. So here maximum stress will be there, okay, up to this level, that is up to this level, and this is the altitude of this positive side, this is the sigma altitude of the negative side. So this type of stress where is acting, that is called alternating stress, means sometimes maximum minimum, or you can see the sinusoidal curve, just like alternating current. Upper part we are taking this as positive, this as negative, so that's why it's a change. Again this is positive, negative, so that's why we given name as the alternating stress. So now, a graph of failure stress against number of repetition of this stress has a typical form as shown. Right? Just now we discuss this one. Next, for some materials such as mild steel, the curve usually known as SN curve or diagram is asymptotic. Just now I explained here, that becomes now almost straight. So asymptotic means what? Right? It's a parallel to that particular axis. If this curve is parallel to the x-axis, right, means it will meet at infinity or it will never meet, then we can say this curve is asymptotic to x-axis. If suppose any curve is there like this and it's a parallel to y-axis, right, then we can say this is asymptotic to y-axis. So here this curve is asymptotic to x-axis, meaning asymptotic to number of repetitions. Okay, so which means that the material has an actual infinite life stress, that already we had discussed about the wire. But what about the alloy, aluminum alloy, that having not infinite, right? So curve for the other material, for example aluminum and its alloy, do not always appear to have asymptotic value, so that these materials may not possess an infinite life stress, right? Already we discussed. So after a certain time that will get broken, so it cannot sustain for the lifetime. Right. Now, concentration effect, that is stress concentration effect, means how much stress will be there, okay, at what point how much stress is acting. Just now we had seen this one, right, alternating current. So here just see at this is the maximum, but what about this one? This is the sigma minimum, right? So at this point when curve will be there, this will be the sigma minimum, this part. So similarly, okay, so how much concentration here it will act, based on that it will be there. So the stress concentration can arise at sharp corner and abrupt changes in section. Means stress concentration, always you can see whatever is starting getting breaking, that started from any tip or corner of that material. So from the corner or tip it is easy to break. Even if you will apply in center, like suppose here this is there, you wanna break or cut from here, then it will be difficult. Better just try from here. Okay, then you can easily cut this part, right? So that's why maximum is at the corner or tip of the material. So stress concentration occur at the corner. Next, like window, rivets, whatever is there, there only you can see these stresses are there. So that's why even sometimes you can see in movie also they are showing that first that if this is a structure and here rivet is there. So first that rivet is coming out, right? After riveting only this got removed and that part got broken. So wherever this tip or edges are there, okay, there most stress is acting on the stress concentration of stress is more. The analysis of stress close to a crack tip using elastic stress concentration factor breakdown. That's what analysis of stresses close to crack tip. So here at the same, in this one, this we can analyze by what up to what is the elastic limit of that material is there. So once they will cross the elastic limit, they will have the deformation, right? And after that, it will starts breaking, not of any shape. So up to that limit, so whatever the elastic limit of this corner is there, that only up to that level only it can sustain, and after that it will break down. Next is, since the assumptions that the crack tip radius approaches zero result in the stress concentration factor tending to infinity, means crack tip radius zero means whatever the crack will be there, right? Some shape will be there, definitely some shape is there, some curve will be there, so that will have the radius of curvature. But if infinite life is there, means what? Where we can say the radius is zero for infinite, right? So once radius approaches zero, then you can say there is no crack in that one. Approaches to zero means there is almost negligible crack, and negligible crack means their life is infinite. So infinite life is there. So means concentration factor tending to infinity. Now, how we will find the stress concentration factor? Okay, so the three basic mode of crack growth is there, right? So let's see here in this equation. First, generally the stress field in the region of crack tip is described by two-dimensional model. So when we are seeing the crack, right? So instead of finding 3D, we are seeing just like suppose this material is there. So at the plane only we are seeing first, and in that plane what happened, and then the crack growth in 3D. That is, if suppose along the first XY axis that crack started, okay, then the growth will be in the 3 dimension, then only growth will start. So first we are seeing that 2-dimensional model only, and then later once the growth will that increases, then it will move into the 3 dimensions, right? This the stress system at a distance r. So suppose from anywhere wherever you are taking distance, just like from here r, right? From a tip of a crack angle length 2a, meaning this is suppose some crack shape is there, right? So this total length is 2a. Okay, so 2m is center will be somewhere a, right? That is this distance is a. Now if suppose more than a will be there, right? From here we are starting, and more than a will be there means up to suppose here the crack will reach. That is radius of the crack is up to this one. Then what happens? Instead of calculating or finding from this side, we can go for this side. So this side it will be less than a. This side it will be greater than a. So better to go with this side. So from this we are changing this side. Now this we can find easily. So that's why it's written there r equals r less than equals to a. This up to this only we can find by this method. Once more than this will be there up to this or before this one, either here, 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 anywhere. So before r equals to a. Once r greater than a will be there, then just change the side, come this side, and it starts finding. So means what? Again you will get r less than. Okay. So now let Fy is the different function for stress and K is the stress intensity factor. So now how they are related? So the C with respect to R, right? When we are taking, then R will be variable and this will be the function. As theta, the same, these two won't be there, means SR and SR, theta won't be there, and here theta will be variable, K and R constant. Next, R and theta both is changing, means what? In first case, only the R is changing. In second case, what happened? Only theta is changing. So now this one is not there for second case, that as theta. So only now earlier this time crack going in this direction, now crack is going in this direction. So that angle is changing. That is the second case. Third case, R is also changing and Theta is also changing. Suppose earlier it was here r at a distance. Now theta changed here. Now this a is there. So in previous also diagram I showed this here, 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 anywhere. So here we are first calculating like this. So here direction is not changing. Theta is same, but only r is different. Now instead of this we are going like this. So now theta is changing, but r still remains same. But now go like this. Theta and r both are changing simultaneously. So the third case will be for the theta and r which change simultaneously. So according to the given value, okay, that we have to this curve, that is the shape of the curve, that crack, this f theta. Once we will have f theta, then SR means r changing, so f theta that time it will be constant. So this leaves all the variations same, just whatever you are considering, that will be the variable, remaining other thing will be constant, and then you can find the value of that. So now K is a function of the nature and magnitude of the applied stress. So already we have seen what is that. K is the stress intensity factor. So it depends on what? Definitely magnitude of the stress. And also the crack size, because its intensity factor by what amount that is getting cracked, or by for once, like suppose once you will apply, so here this crack is there, so this much size is there, you are applying 2 kilonewton load, or based on that stress 2 kilonewton per meter square. So now this crack is there for 2 kilometer, every 2 kilonewton meter per meter square, that is stress, you will get this much crack. Now suddenly you are applying 6 kilonewton. What happened? So this crack will be 3 times of that one. So how much stress is applied, based on that the intensity factor that will get changed. Right? Now this term 2 pi r, actually this is here, this is pi, not p. This is pi, 2 pi r power 1 by 2 is, and f theta maps the stress field. This already we have discussed. This is the stress field, that curve of this one, in the vicinity of the crack, and are the same for all cracks. So see here, the term 2 pi r power 1 by 2 and f theta maps the stress field in the vicinity of the crack and are the same for all crack under external load. So because of the external load, these two values will be same for every one. That causes crack opening of the same time. So when same, because of the same reason, if crack starts, then these two will be constant. Only the what intensity factor will be different. Now fluctuating stress. So according to the name itself, fluctuating is what already we had seen the minimum, that this type of curve. So this is alternating. This is not the fluctuating, right? But still, if you can see, this is changing here. This is changing here. Or fluctuating is sometimes this much amount of stress is acting, right? Sometimes this only, sometimes this. So this is right, comes under the fluctuating stress. Means sometimes suddenly more stress, suddenly less stress. It's not like that in regular pattern that stress will act, and that is called the fluctuating stress. So what? Atmospheric turbulence and the cabin pressurization cycle are only two of the many fluctuating stresses. So means which one is there? Atmospheric turbulence. Don't know when atmospheric turbulence, that when suddenly high speed air will come or low speed air will come. That low speed air is stream, right? So that is the fluctuating stress. Sometimes it's coming very lesser amount. Sometimes it's just in the form of cuts. That is huge amount, right? Next is cabin pressurization. So at the ground itself, we are pressurizing the cabin, that where we are sitting in the aircraft, right? So that once the flight will go up in the atmosphere where the pressure is lesser than, then also we are not feeling any issue. We are comfortable in that. Means whatever the pressure is required to us, we are maintaining in that cabin. But at the once that flight goes above in the sky, then the pressure outside of that aircraft starts reducing, and because of that, sometimes inside of the aircraft also is getting reduced. So that cabin pressurization is getting changed, right? So many fluctuating stress that cause fatigue damage in aircraft, right? So many fluctuating are there, but these two are what? Which damage the aircraft. Next, on the ground, the wing is supported on the undercarriage and experiences tensile stress in its upper surface and compressive stress in the lower surface. So when they are in the what, in hangar or some, suppose that is not in use that particular time, then what happen? Okay, that wing is this one, right? For the aircraft, both side wing will be there. So this, because of their self weight, again that will starts deforming, right? That we will see in the next module, how the strain will be there, and because of that, why is strain energy method. Okay, how the weight load will affect, and because of the weight load, how much deflection will be there. So this, that means this should not, that whatever the weight of this wing act vertically downward, the same weight should support this one, so that no deformation should be there. So once we will apply this force, then what happen? The upper surface stress, what, compressive stress, because we are pushing upward, right? And the lower surface is in the tension, right? So lower surface experiences tensile, and upper surface experiences the compressive stress. In flight, these stresses are reversed as aerodynamic lift supports the wing. This, now once it's start flying, then what happen? Body is moving upward, right? So upward means the shear. Now this is the wing. So now we are applying load here in first case. So now what happen? This will try to move upward. So this upward is getting contracted and the lower part is getting expanded. So this is experiencing the tensile force, and the upper part is that experiencing compressive force. Now if once this will going up, means now load is acting from this side. So this upper surface will experience the tensile force and lower part is getting contracted. So this experiences the compressive force. So at the ground, just opposite to the flight. Also, the impact of landing and ground maneuvering on impact surfaces cause stress fluctuation. So impact of landing and ground maneuvering. So in the ground maneuvering also, that are like taxiing, okay, and towing. So these are also affect the what, fluctuation of the stress. While during the landing and takeoff, flaps are lowered and raised, producing additional stress in the flap support structure. So that again is the what, fluctuating stress, because in overall body that stress was not acting that time, but suddenly at the time of landing or takeoff, that flap is open. So because of that also the stress is created. So for that instant only that stress is there. So that is also at that time more stress is there. Yes, again that is the fluctuating stress. Next, engine pylons are subjected to fatigue load from thrust variation in takeoff and landing. So engine pylons, whatever you can see, that back side is there, they're safe, right? So that also, because at the time of landing and takeoff, those requires maximum energy. Yes, they are at their maximum level. So, and during the level flight, that is the normal. So again, that what increased at the time of landing and takeoff. So that is again the fluctuating stress. Also from inertia load produced by lateral gust on the complete aircraft, right? So now just this word is there, lateral gust, right? So over the surface as air will pass, or over this one, that will create a gust. Because of that gust is there, because of that air load, right? Or air hitting to the aircraft surface. So because of the inertia, right, that also produces the fluctuating stress, because depending upon the shape of the aircraft or shape part where the stress, that air is hitting to the surface, based on that, then that means the stress will be there, and hence we can say the pseudo of the body the stress won't be same, and hence that stress is also but fluctuating stress. Now for finding this only, the Goodman and Sullivan given some equation, they modified according to that what we had seen in the stress strain curve, right? So now just see, this is sigma w, and that is written here, right? Or in this next video, let's see. So this is sigma L, sigma B, sigma T, sigma M. So sigma M already we had seen, that is the minimum. Sigma amplitude minus sigma T. This line is sigma A minus sigma T line. So this line, the lower, this line is the Goodman line, and this the curve one is given by Gerber's line, and this one Soderberg line. So combination of these two, only these two we have to see, the combination of these two, right? So that's why after this we will see this one. So first here, these two almost it's the same. You can just see here the thing is only in this Goodman used sigma b and Soderbergh used sigma y, right? And they got the same straight line equation, and hence they just given their two names. Soderbergh used the yield stress, and this is the maximum stress of that one. So now after seeing this one, what happened? Goodman modified that line, right? So buckling stress becomes ultimate stress. Now we change to, instead of buckling stress where it will buckle, no, they give no, it's the ultimate stress, right? So now this buckling stress they change to ultimate stress, means up to what point it will get break or broken. Sorry, this actually should be here. This is the sixth reference number. This is not. So this is sort of a diagram, right? So after seeing this only they modified. No, instead of the buckling only, why not? Let's find till the what breaking point of any material, right? So what is the relation? So the Goodman-Soderbergh diagram is an equation used to quantify the interaction of mean and alternating. You see here, mean and alternating stresses on the fatigue life of a material. So how much mean is there, and after that how much alternating, the previous one, that alternating stress, this was there. So mean and in that. So from those curve, that is from this curve only, right? Sigma mean and alternative. So from here to here, above the mean is the alternating, this one. So from there only they find the relation, and who found that? Goodman and Soderbergh. So after predicting that one, they given equation what? Sigma m by sigma b plus sigma a by sigma w equals to 1 by n. This is the Goodman line. So this is what? The equation of a straight line having the x-intercept and y-intercept. Just like x by a plus y by b equals to 1. So here a is x-intercept, b is y-intercept, and this one. So similarly from here, this is what? Intercept of maximum. This is intercept along sigma a. So this again will give the equation, that is straight line only. So after putting the values, once we will plot, we will get the straight line, and that already we are seeing in this equation. So this is the straight line. Yes, just seeing the difference. This is just sigma b and this is sigma y, and remaining everything is same given by Soderbergh. So just see where sigma is the stress amplitude, sigma m is the mean, sigma w is the fatigue limit for completely reverse loading, sigma b is the ultimate tensile. So thus we are seeing the for modified ultimate tensile stress, and this is for yield stress, right? So the difference is they just Soderbergh found for the yield stress, means this is for ductile material just like rubber and all, and this is the they found for mild steel where sigma b is more. Now, so difference between Goodman and Soderbergh. Just now we had seen what is that. Soderbergh line A is straight line joining C on the ordinate to twist on the abscissa is called the Soderbergh line. So just here, this one, right? Okay. Now Goodman line is straight line joining SE on the ordinate to SUT. So SUT is ultimate here. SUT. So this is what? Goodman line, and this is SY, and this one. This is the Soderbergh line. Clear? So it's just relation between what they are taking. They just use that Soderbergh used the yield point and that yield stress, and Goodman used the ultimate stress, or you can say Soderbergh for the fragile material, or having which one having up to the plastic limit only it got broken, and Goodman found for the material like steel. Now cumulative fatigue damage. So cumulative means what? Just add everything, just like in the statistics we are finding. Suppose frequency is there 5, 8, 7, right? And then we are finding the cumulative frequency. So first this will be find Now this will be 5, then 5 plus 8, 13, and then 13 plus 7, 20. So this is the cumulative frequency at this point, whatever will be there. So for this will be the cumulative. For this 13 will be the cumulative. So this cumulative is overall how much acting on that one. So cumulative fatigue damage theory can be stress dependent or stress independent. Right? It's not necessary that it will be dependent at that time stress is acting or not, because it's a cumulative sum of all. Suppose here for the fourth it's a 0, right? Or 0 frequency is there. Then also what happened? 20 will be there. It's not like that here it's a 0 frequency is there, means overall this will be 0. No, this will be 20. So that's why it's a dependent or independent. So this is the dependent case and this is the independent case. The amount of fatigue damage. So how much it's the damage? It's a independent or maybe dependent also, produced by a specific fraction of the number of cycles that would produce failure can be same for all the stress amplitude. So that time if stress is same, you can say stress independence, or if it's a different, then it's different, but that means stress dependent. So different, once different will be there means definitely stress is acting over there. So that's why it's getting damaged. So damage means it's depending on stress. Once you will apply the stress and damage is getting increased, this is depending on the damage, that is stress. And if even after applying that also damage is not getting changed, then we can say that is the stress independent. Right? Now cumulative damage factor is fatigue, crack, or the amount of structural fatigue line from pavement that has been drained. So how much is there based on that? It's just simply damage factor, any factor how it will get affected. So it's expressed as a comparison between the repetition of applied load and the repetition of possible burden of failure. So just see repetition of applied load. This one is important. That factor is repetition of applied load by repetition of possible burden. Possible burden is what? What is the chances of getting failure? Right? If more number of, that is more amount of stress will act, chances will be more. Right? So that is only the cumulative damage factor. Suppose once you applied 5 kilonewton load, right? After some time you applied 10 kilonewton load. Now overall how much applied over there? 15. That is the cumulative load. So because of this, how much chances are there? That means this time how much burden that not experienced. Ratio of those two is the cumulative damage factor. So with this, we'll stop this video. So if you have any doubt, you can just post in the comments or you can just contact me regarding the doubt clear. So we will see in that one. Okay, so theory portion of the first module is over. Right. After this, we will see the numericals related to this module. In our next video, we will see the numericals related to this video. That is this module.
Like, share and subscribe. Hit the bell icon for more updates.